Precept 3, spring semester 2016. In this precept, we're going to discuss a few concepts. Let's take a look at some of those concepts. Dijkstra's partitioning, notice it's not sorting. It's one of those things that you would do when you do quicksort with duplicate keys. We'll discuss comparators, we'll discuss sorting invariants, and then finally we do a bonus problem of three-way merge sort. So the first problem we want to think about is what's called the partitioning problem. Now, why is partitioning problem very important? Let's take a look at an array that contains all duplicate keys. If you apply the two-way partitioning algorithm in order to do quicksort, you would choose a pivot and you would go through this and try to find where the pivot is. Essentially, the pivot will end up here. So the next one, you're going to go through this. You choose a pivot, you go through this, and find out where the pivot is going to end. So if you think carefully, this is not a good algorithm, because you may be doing n operations in the first round with an array of size n minus 1 in the second one, and so on. And we know that we have learned that this reduces to tilde 1/2 n squared. So essentially, this is the worst case of quicksort when you have duplicate keys. So what we're going to do is to find another way to partitioning, which we call three-way partitioning. So the three-way partitioning idea is that given a pivot, we always choose the first element to be the pivot. We're trying to find a group of elements. If all of them are equal, it's going to be all here. All the equal elements will end up here. LT will indicate the first instance of the pivot. Let's suppose pivot is A. GT will indicate the last instance of pivot. Anything less than LT is strictly less than the pivot and strictly greater than the pivot. Now, if you compare that to the two-way partitioning, what you will get is you get the pivot in the right place, but you're going to get anything less than or equal to here and a greater than or equal to here. This means it's possible that there could be other pivots on these sides. And in a case like this, it can behave very badly. So imagine if you have a three-way partitioning where we can get all the A's into one place after we do one partitioning, then we're going to be doing really good. Because if you think about an array that has all the equal elements, then you're going to get all the A's into this group, and you're not going to have anything here or anything here in this particular case. So in other words, you can do the partitioning in linear time. We can always do partitioning in linear time, but because you don't have anything on this side and this side, you can actually do the sorting in linear time. So how does this work? There are three things that we will consider. We call this invariant. In other words, as we move these LT pointers and GT pointers, we need to make sure that this invariant is satisfied. Anything LT is the first instance of the pivot, and then at the end, GT would be the last instance of the pivot. And these are the conditions under we will be doing the swaps. So in other words, if you have a specific I, so if you have a pointer, let's suppose you have an I pointing to something, if S of I is less than the pivot, suppose this is less than the pivot, then we should exchange S of LT with S of I, so that S of I comes to the left of the pivot. Remember, the LT is the first instance of the pivot. If S of I is greater than the pivot, then we want to exchange that with the GT. And you will see this when we do the example. If AI is equal to V, increment I, when I is strictly greater than GT, then we're going to end this algorithm. So let's apply this algorithm to this particular thing. So what I'm going to do is I'm going to have a pointer LT and I here, and the pointer gt here. So in this case, a of I, which is r1, is equal to the pivot, so I need to increment I. Once again, a of I equal to the pivot, so I need to increment I. At this point, a of I is e, which is less than the pivot. E is less than the pivot, so I need to exchange a of lt with a of I. So I'm going to have e here, and r1 here, r2 here, and you increment both lt and I. So the lt would come here, and the I would go here. At this point, a of I, which is a, is less than the pivot. So we need to swap that with a of lt. So the a would come here, r2 goes there, r1 goes there. We increment the lt. Apologies for that. We increment lt, then we increment I. At this point, a of I is L. L is less than the pivot. Pivot is the R. This is our pivot. So because it's less, we have to swap it. So we're going to swap with the A of L, and LT actually improved to here. So LT would be here. So at this point, we're going to swap that with L. So we'll have L here and R1 here, and the R2 would be here. And so the LT is incremented to this, and the I is incremented. Now S is bigger than the pivot, so we get into this condition where you're going to exchange A of I with A of GT. So this means these two elements are going to be exchanged. So you're going to get T here and S here, and the GT is going to be decremented. At this point, you look at A of I, which is T, which is greater than the pivot. So this means that we have this condition, so we have to swap A of t and the pivot. So the R4, in other words, these two are going to be swapped. And therefore R4 comes there and the t comes here. And the GT gets decremented. This point, GT is pointing to R3, I is pointing to R4. Because A of I is equal to the pivot, I is going to move forward. Now A of I is O, which is less than the pivot. So what we need to do is to swap that with the first instance of the element. So we're going to swap this one and this one. So we're going to get O here and R2 here. And then our LT pointer will move to the next one, and the I will move here. At this point, A of I is equal to the pivot, and therefore it's going to move forward. And therefore, I is greater than GT, so we're going to stop the algorithm. So we'll have R3 here, and so the final answer is going to be R3, T, S, R2, R4, R1, and we will have O here, L here, A here, E here. So note that all the pivot elements are here. This side is strictly greater than the pivot, and this side is strictly less than the pivot. Now keep in mind that we are not done with the quicksort. We have to apply quicksort again to this side and this side in order to get a sorted array. This is just the partitioning part of the algorithm. Our second problem deals with comparators, which is another interesting concept from Java. The comparators allow us to pass any kind of a custom compare method to a class. To demonstrate that, let's take a look at one of the known classes that we always work with. So the class I want to show you is called the point2d. So in the point2d, it implements the comparable interface on point2d objects. Point2d is custom objects. Point2d has two instance variables, x and y. Now the key idea here is that because it implements comparable, it is important that you're promising a contract here. You're promising the world or someone who adopt this method that you would provide compare2 function. This will allow any kind of point 2Ds to be compared. So in this case, as you notice, it compared by the y coordinate and then compared by the x coordinate. So if any class implements comparable, this means that you must have a compare2 method. Now, there are other interesting ideas in this code. An interesting idea, there are a number of these things, is that can we have some private comparators? So this would be compare2 would be our natural comparator. That's the natural way to compare things. But you could have custom things. Like, for example, you only want to sort by the x coordinate. So we need to have a comparator called x order. So we implement the interface comparator. Now the comparator requires you to have a method called compare, which only takes 2 arguments and then return -1, +1, or 0. Note that it is a private static class called the x order. So therefore this class is not available to anyone outside. So how do we provide this comparator to a client who wants to compare elements of point 2D? We do that through a public, in this case it's a public static final comparator variable called x order. So in other words, we can just say point 2D dot x order. Because it's static, I'll be able to refer to this instance variable through a point 2D instance. And we call a new x order. This is the private class, if you recall. It's the private class that allows me to create a comparator that I can pass into a function. So let's go back to our question. So in the question, we are asking the following. We are asking the question that if one implements comparator, so here's the question we are asking. We're asking the question, if a Java class implements comparator, or comparable in this case, what method must be provided? The method that's provided with a comparable interface is compare2. It only takes a single argument. If a Java class, specifically a private Java class, implements comparator, like in the x order, then the comparator must implement something called compare, which will take 2 arguments, x and y, and compare and return. So what's the difference between this and that? Why is this taking only 1 argument, this taking only 2? That's because the comparable is called from one of those objects which call this. So this compared to that would give you something else. So here we're sending a comparator which would take 2 of these, the same objects, and then try to compare it. So this is the key idea in these comparator things. Now, so here's an example of some sort of a comparator that we're going to implement called a distance comparator. Notice in this case it's a public class. It could have been private class, but it's a public static class. Now what we are trying to do is the following. If you're given a set of point 2Ds, suppose you're given a point P and a point Q, and then we are trying to find the distance from a third point. Let's say the third point is O. We want to find the distance from that to P and the distance from that to Q, then use that as a way to compare 2 things. So in other words, that we will have a point 2D and a point 2D, and P and Q will take the distance to some point here. So in this case, let's assume that we call that origin. So let's have an instance variable called origin, which is a point 2D. It can be anything. It doesn't have to be origin. It could be, doesn't have to be 0, 0. It can be anything. And a distance comparator, what this will do is it'll take a point 2D. So let's call it X. You can call it anything you want. And then what we're trying to do is when you create a distance comparator object. It will use the constructor. This is the constructor for the distance comparator. And then it will take an argument through the constructor, provide that argument, a copy of that argument to the origin. And then we will use that origin as a way to take the point P to the distance to the origin. And the same thing here. In this case, we're going to be comparing the ascending order. So if this is less, then we would make it -1, a +1, or 0. Now keep in mind that this comparator can be used to sort the points by the increasing order from another point. Now, clearly I could change these to +1, -1, and 0 and reverse that. So I can have a reverse distance comparator which will compare in the reverse order. Now, the parameter I want to send to the comparator is a point 2D. Now, suppose we want to use our comparator to sort a list of points. So let's suppose we get a set of points, put them into an array. We create an origin point. It can be anything. It doesn't have to be 0, 0. Let's say it's 2, 2. So we want to know from point 2, 2, how do we compare distance to P, distance to Q, and then we kind of do this through that. So in this case, what we're going to do is we're going to say, okay, let's get a new object. So the object is called distance comparator. Notice the constructor requires you to send a point. So I'm going to say this new distance comparator. And then the point that I'm sending would be this origin here. And then when you want to sort it, all you need to do is just put this object in here. This is the object that you're providing to the Java array sort. Now in the array sort is called which sorting algorithm Java uses. Now we know that if they are objects, in this case they are, that Java uses the mergesort to do this. This is the internal Java sort. Java also uses quicksort in some cases. But in this case, it would use a mergesort. Mergesort is consistently n log n. It's a very stable, guaranteed sorting algorithm n log n. In some cases, it's better than quicksort because quicksort can display worst case behavior of n squared. So the third problem is one of those standard problems you will find in many midterms. The problem gives you a bunch of things that are unsorted, and it gives you the things that is sorted. And it gives you a bunch of inputs or a bunch of sets. We call them intermediate steps of one of the 6 sorting algorithms. So if you take this, it could be mergesort, top-down, quicksort, maybe quicksort 3-way, it could be insertion sort and sort. So your job is to find out which algorithm it seems to be applying to get this intermediate input. Now to answer that question, let's just go to the following. Let's just think about the invariants. Insertion sort invariant is that the first part of the array is sorted in the middle of the algorithm, and the last part of the array is the original. We haven't changed anything. Selection sort kind of messes it up a little bit. It has the same invariant as the insertion sort. The first part is sorted, but we also know that they are the minimum elements. All the minimum elements are in the right place. So none of these elements are going to be disturbed when we are doing the next set of iterations. Now in the mergesort part, we have to look for, this is the mergesort, bottom-up mergesort code, which is iterative. The goal here is that you're looking for grouping subarrays of 2, then arrays of 4, then arrays of 8, then arrays of 16. They get all merged in parallel. So it's a great parallel algorithm that can be implemented. The top-down mergesort uses recursion. So it's try to sort from low to mid, the left-hand side, and the right-hand side. Then it applies the merge algorithm to get the two things merge. So if you sort the left-hand side, then the right-hand side, I can just merge them. So a few things that you have to remember is when you do top-down, if you split it into half, 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 when you get to the final stage, 1 and 2 get merged first. They may have just a single element. You get a sorted array of size 2. Then 4 and 5 gets merged. So your order is going to be, if you look at in the middle of a top-down, you will see this part sorted, and maybe some of the smaller segments onto the right are sorted, but none on this side are even touched. All right, so given this knowledge, let's just try to go back and try to figure out exactly how this works. So there are a few things that are really important here to note. We just say that actually this should be not 8, should be 6. There's only 6 sorting algorithms we have to worry about. Okay, so let's think about each one of these algorithms. Now, if you think about this algorithm, we can kind of see that the groups of 4 have been in the right place. They've been sorted. So we have the groups of 4 sorted, which sounds like the bottom-up merge sort. So I'm going to write 5 here. Now notice those groups of 4 are the same group. These are the original things, and then they have been put into the right place. So that's how the bottom-up merge sort works. If you look at this one here, you will notice that you have to carefully look at this. You'll notice that this part here is completely sorted, which is equal to the unsorted part here. And then you will have groups of 4 sorted. So this looks more like a top-down merge sort, which means that you have these sorted. They have been in the right place. Notice that they have been sorted here, and this is sorted. So this is in the intermediate step of a merge sort top-down. Notice the difference between top-down and bottom-up. In the top-down, you could have a twice the size array sorted. In the bottom-up, your arrays are going to be all the same size. The next one, if you look at the next one, the next one's going to be, if you look at from here to here, that would be the same as the original set that you have here. That means we have been sorting the original parts of the array, and this part is untouched. It is the original thing, which we call the insertion sort. So that's 3. If you look at this one here, you will notice that this part, these are the minimum elements in the array, and these are all bigger than this. So the only way that can happen is you have a selection sort. Now in this case, if you look at night, the night has come here. So all the things that are bigger than night on this side, less than night on this side. This means this has to be one of the quicksort. Same thing here. This has to be night actually. So the same thing there. So it has to be this greater than, this less than. But in the quicksort standard one, it's less than or equal to, but unfortunately we don't have any duplicate elements of night, so you're not going to be able to see that. So how do we differentiate between these two, whether it's a 3-way or 2-way quicksort? Now one of the things you want to notice is that in the 2-way quicksort, it leaves the original elements that were less pretty much not touched much at all. So Denny, Dent were all left in the right place. Some things get changed, but for the most part, it leaves them alone. So the quicksort 2-way does fewer swaps, but the 3-way does a lot of swaps. So if you actually apply the three-way Dijkstra's quicksort, you will see that there's a lot of stuff happening here.
Okay,
So
so
that's one of the
let's
ways to
take a
do
look
this,
at
but
the
you can
bonus
practice many
question,
of the midterm
which is the
problems
three-way
that
merge
appear.
sort. So the question here is that given three sorted subarrays of size n over 3, how many comparisons are needed to merge them to a sorted array of size n? Now we know the merge sort deals with two subarrays of size n over 2, and it has a complexity factor of n log n. So let's take a look at what we can do. Suppose we have three arrays of size n over 3. So I could do the same thing I do with the merge sort, the two-way merge sort. I compare one element here to one element here. And so a total of, so each element requires one comparison. So since we have two n over 3 elements among these two n over 3 subarrays, you would need 2n plus 2n over 3 comparisons. And then I'll have to take this 2n over 3 array and then combine that with another n over 3 array. So this means that I'll have to compare this with that. So that's going to be another total of n comparisons on the top of 2n over 3 comparisons. So we have a total comparisons of 5n over 3. Now that's method 1. What is method 2? Method 2 says, all right, so what if we do the following? Rather than doing two at a time, we'll just compare one here, one here, one here, and find the minimum and put it here. Now to do that, you have to do two comparisons. You compare this with that, and then take the smaller one and compare with this, and find the smallest of the three, and then insert here. So this means to place an element, you need two comparisons. Therefore, to place n elements, you need 2n comparisons. So the method 1 takes 5n over 3 comparisons. Method 2 takes 2n comparisons. So if you have to choose between the two, I would go with this one because it has less comparisons than 2n comparisons. So in any case, let's think about how to look at the complexity of this three-way merge sort. Now we can describe the three-way merge sort using a formula like this. We can say that the cost to merge sort an array of size n would be to three arrays of size n over 3. That's the T of n over 3 is the cost to merge sort an array of size n over 3, plus some constant times n. That's the linear number of operations you have to do, where C can be either 2 or 5 over 3, depending on whether you choose method 1 or method 2. Now, if you replace T of n over 3 by this factor here, this means that you can replace the n by n over 3. You're going to get the, if you simplify this, you're going to get 9 times T of n over 3 plus 2cn. And then if you do it one more time, you're going to get 27 Tn over 27 plus 3cn. Now you can see the pattern here. So what you're going to get is after k splits, you're going to get 3k Tn over 3k plus k times Cn. Notice that 3 times Cn, 2 times Cn, and so on. So if you assume that n is 3 over 3 to the k, like before, you're going to get T of 1 here, which is going to be just some unit cost. And k is going to be log 3n Cn. And then you can say it's going to be Cn log 3n, where C is going to be either 2 or 5/3. So the next question is, which one is better? So in a two-way sort, merge sort, C is equal to 1. In three-way, no matter which one you choose, it's going to be a bigger factor. So although they both have the same complexity, which is n log n, the factor, the constant factor, makes a difference between three-way and two-way. Therefore, I would choose two-way in all cases.